Can everyone see my screen?
Yes.
Okay. Thank you, Dr. Shu. Okay, so hello everyone. Today I'm going to be giving just an overview about the work I've been doing on surfactant-enhanced epitaxial growth for quantum dots and quantum photonics. And so just a brief personal introduction. I got my bachelor's in electrical engineering at Ain Shams University in Egypt. Then I was briefly enrolled in the physics master's course in the American University in Cairo, where I worked on nanophotonics. And now I'm pursuing my MASc in engineering physics as of 2019, working on epitaxial growth under the supervision of Dr. Ryan Lewis. And my research interests are mostly epitaxial growth, quantum nanostructures, but particularly for quantum photonics and nanophotonics in general. And so this is a iconic picture of Cairo, my hometown, capital of Egypt. I'm originally from Egypt, but I spent around half my life in the UK, so I guess I'm from both places. But this is just a picture of the iconic pyramids and the dome of Cairo University. And so just shows you how old really the city is. And this is another picture taken a few months back of me. And behind me there, that's the Suez Canal, which has been quite pertinent in the news recently, but thankfully the ship isn't blocking it anymore. And yeah, so just an overview of the group. It's the Epitaxial Nanostructures and Materials group headed by Professor Ryan Lewis, as I mentioned. And basically, the group is mostly interested in epitaxial growth and, for example, investigating quantum nanostructures and phenomena and materials and strain, for example, in these materials using epitaxial tools. And mostly the applications that the group is focused on is, for example, applications in biosensing, which is pertinent, as we know, due to the pandemic that we're living through. And for example, it's also interested in optical interconnects and quantum optics, as we will be seeing a bit further in the presentation. This is a photo of the MBE system, one of the main tools that the group uses. And so just to briefly state the objective of the project. The objective is to investigate the role of surfactants in altering gallium arsenide growth and the one-on-one orientation in particular. And the aim is to alter the surface morphology, for example, by being able to grow quantum dots on or create smooth surfaces on this substrate. And this is because this substrate has some interesting properties which allow us to create some interesting photonic devices, as we'll see later in the presentation. And so just a quick outline. First, I'm going to go over a bit of the background, for example, talking a bit about surfactants and epitaxial growth and quantum technology. Then I'll be going into the work I've been doing on MBE and MOCVD, Molecular Beam Epitaxy and Metal-organic Chemical Vapour Deposition. And then I'll be going more into the future work of how we can build on the work that I've been doing using MOCVD and other techniques. And so just a quick background. So quantum technology is this really promising, it's one of the really promising industries and really hot topics that's been gathering a lot of steam recently. And so we've heard of, for example, the advantages of quantum computation, cryptography, networks, sensing. There's many applications. But I want to briefly just focus on this notion of the quantum optical network, or maybe the quantum internet, if you will. And so basically, it's similar to a classical network, but you have, instead of classical nodes and classical channels, you have these quantum channels and these quantum nodes. And so, for example, you can imagine a network of qubits or quantum computers, and they utilize, for example, instead of normal switches, quantum repeaters, and things like that. And basically, it's the ability to share qubits rather than classical bits using these quantum channels. And so you can imagine these flying qubits, for example, which are like photons being shared in this network. And the main interesting thing about this network is it's the core really of quantum networks is this ability to utilize entanglement. And so you can imagine, for example, entanglement giving a lot of benefits, for example, for quantum communication. So for example, you can imagine very secure communications where the two bits are entangled and thus it's hard to eavesdrop, for example. You can imagine, due to the peculiar properties of entanglement, you can imagine maximum coordination or synchronization between two qubits. So that's interesting for applications that need synchronization, for example, like quantum clocks. And so it's a really interesting field. And the quantum technology market is has been estimated to be worth $532 million in 2020, and is forecasted to reach 3.2 billion by 2030. So it's definitely growing fast. And so this is a picture, for example, of a quantum light source, and in fact, a quantum dot-based quantum light source, which is interesting. This is out of a startup based in Paris, France. And so this technology is already being commercialized. And of course, for these quantum networks, we're going to need quantum light sources. So you can imagine entangled photon sources or single photon sources, for example. And so this also translates well into the world of academia and research. You can see in this map all the different, almost all the main economies and countries of the world are really pouring money into this quantum technology effort. It's been estimated that the money pledged so far is around 22.5 billion as of 2021, pledged on the long term. So it's a really hot area and has some interesting applications. It's already being commercialized. And so I want to look here about quantum dots and how they can be used as these entangled photon sources, which can open the pathway to these quantum networks, for example. And so basically, a quantum dot is this quasi zero-dimensional nanostructure. It's been referred to sometimes as an artificial atom. So you can get these distinct like energy levels, or rather than just like in bulk. And so for entanglement, the key thing to realize here is that entanglement, you need to have really indistinguishable particles. So there can't be any like degree of freedom between them that's different. And so in quantum dots, how this occurs is that, for example, if you look at this energy band diagram, you can see that how this occurs in quantum dots is this bi-exciton-exciton cascade or recombination. Exciton is just this quasi-particle that's just an electron and a hole bound together based on Coulomb forces. And so what you can see here is that if this intermediate level where the bi-exciton is going to relax into exciton, if these two intermediate levels are different, then you're going to get emission of different photons with different energies, and so they're not going to be indistinguishable. So it's going to be hard, really, to create this entanglement. And so this asymmetry in quantum dots can really kill its ability to create entangled photon sources, or entangled photons rather. And so what we want in our quantum dots is them to be very symmetric. And quantum dot sources for entangled emission are actually pretty advantageous because they're easy to integrate with the current mature semiconductor processes that we have. They're simple as opposed to atomic sources, for example. No need for like this trapping and stuff. And it's deterministic. So with a photon trigger to trigger this cascade, we can get the photons. And basically, indium arsenide, gallium arsenide quantum dots are like the main material system to realize these types of entangled photon quantum dot sources. And so the conclusion here is symmetry is key. And so, okay, now we want to know how to grow these quantum dots. And so just for epitaxial growth in general, we have these several epitaxial growth modes. So for example, we have the 2D layer growth mode. And so depending on the surface energy considerations between the substrate and the layer we're growing, we can get different growth modes. And so we have this 2D layer growth mode where the surface energy of the substrate is higher than the layer. The growth proceeds in this 2D fashion. And when the opposite is true, we start to get these 3D islands. And the main mode used for quantum dot formation is the Stransky-Krastanov mode. And so depending also on the energy considerations, you start to get this 2D wetting layer when we're growing. And then you start to get these islands growing on top of it. And so it's a mix, it's a hybrid mode maybe. And these islands form the quantum dots that we want. Surface energy is just basically the energy needed to create a surface. And so if we look at the growth of indium arsenide and gallium arsenide, this is the material system we want to use, we see that for gallium arsenide 100 orientation, as we can see here, this is the zinc blend structure, you can see here the 100 orientation. You can see that the growth occurs naturally in this SK growth mode. So we get a wetting layer, then we get strain relief in the form of quantum dots, so we get the wetting layer plus quantum dots. This is a AFM, atomic force microscopy image of quantum dot on gallium arsenide 100. But for 111 though, we have two problems because first of all, it proceeds in a 2D fashion, so we're not going to be able to get quantum dots naturally without intervening, and it's also quite rough. So there are two main problems really with gallium arsenide 111 growth, and this is just how the plane looks like. And this is a shame because gallium arsenide 111 has a very high degree of symmetry. And this is predicted to be ideal, again, for this quantum dot entangled photon source. And also, gallium arsenide is also useful for a whole host of different applications. So for example, it's been used as a base for topological insulators, spintronics, and stuff, but we're focused here on quantum photonics. And so this gallium arsenide 111 surface, again, why is it rough? So why is this surface, we know it's 2D, we know it proceeds in a 2D fashion when we're growing on it, but why is it rough? Well, it's rough, as we'll see. First, let's see how rough it is. We can see that from this AFM image, you can see at its roughest, at its highest point, it's 40 nanometers. So you can see quite a lot of roughness. This is just gallium arsenide, just homoepitaxy. It's in the range of micrometers, these hillocks. And so this could be attributed to this energy barrier for downhill diffusion known as the Ehrlich-Schwabel barrier. So you can imagine here these atomic steps, and this atom is falling on the surface. And instead of diffusing downhill and creating this normal 2D growth, it's sticking to the top because it can't diffuse downhill due to this Ehrlich-Schwabel barrier. And so this Ehrlich-Schwabel barrier really promotes 3D growth. So this isn't good, of course. And so, well, how can surfactants, what role do they have in changing this reality? Well, surfactants basically, just as a definition, they're just a name given to atoms or compounds or whatever that when used in the growth, they can alter the surface energy. And so that means if we use them, we can alter the surface energy. That can thus alter the growth modes, as we mentioned at the start of the presentation. And so they're very advantageous in changing how the growth occurs on the surface. A key thing to note is surfactants, we don't want them to be soluble in the bulk. We want them just to float on top of the layer being grown. And then once the growth is finished, we want them to dissolve or to evaporate, if you will, from the surface. And so the most famous surfactants for 3,5 growth is antimony and bismuth. And basically, that's what we'll be using in the research. And so this is just a bit of literature review here. We can see that this bismuth as a surfactant has already been used on the 110 surface for indium arsenide, gallium arsenide growth. So this isn't homoepitaxy. This is growing indium arsenide and gallium arsenide. And so gallium arsenide on 110, when we're growing it, it proceeds also in a 2D growth. We want to be able to use it, the SK growth mode on it to get quantum dots. And so as we can see here, this is a AFM image of indium arsenide, relatively smooth. But then on gallium arsenide 110, but then when we grow with bismuth, simultaneously with the indium arsenide on the 110 gallium arsenide surface, we start to get these quantum dots. You can see up to 8 nanometers high, for example. So bismuth with enhanced deposition manages to induce this SK growth mode on the quantum dots. And there are no traces in the bismuth. This has been verified. Of bismuth in the quantum dots has been verified by energy dispersive X-ray spectroscopy. So all the bismuth dissolves. And they're also found to be optically active. So you can actually use these as photonic sources. And so you can see here the photoluminescence done without bismuth. You just get a response of probably the Wang layer. And then after that, you get, with bismuth, you start to see these sharp transitions, which are indicative of optically active quantum dots. And so the takeaway here is that bismuth has been used as a surfactant on 110, and it has successfully induced a change from the 2D to the SK growth mode. And so we know it works basically on this surface. Okay, so that's now we're going to go into the work that I've been doing. And so I was probably the second student to join the group, and I was the first to use the bismuth. So I had to do some of the calibration to start using bismuth for the first time in our experiments. And so this new bismuth source in the Molecular Beam Epitaxy machine, we needed to find a relationship between the flux and the temperature, because we want to know what temperature should be applied to the bismuth diffusion cell to get a certain flux of bismuth. And so what happened was we deposited bismuth with a certain temperature on just a normal silicon wafer, and measuring the volumes. These are bismuth, this AFM image of the bismuth deposited on the silicon. And so using some image analysis, calculating the volume of these droplets and knowing the density of bismuth, we can now know the atoms of bismuth, how many there are. And so knowing this relationship between the temperature and the atoms, we can know the temperature between the temperature and the flux. And so knowing the pressure versus temperature relationship and this data point, the single flux data point between temperature and the atoms deposited, we can start to get a picture or a calibration for what temperature to apply in order to get the flux we want. So we've calibrated the bismuth source. So now it's time to start using bismuth on gallium arsenide 111. And so what we did was we did homoepitaxy. So we're not using indium arsenide yet. We're just seeing bismuth and gallium arsenide, just homoepitaxy, growing a gallium arsenide buffer layer and seeing how it affects the surface. So we just want to see, can we use it to create a smooth surface, for example, before we even start using in-house and quantum dots. And so what happened here is that we used a temperature of around 350 Celsius. And what we saw here is that bismuth actually stuck to the surface. The temperature is too low for bismuth to evaporate or dissolve. The desorption is heavily dependent on the temperature. And so what happened was this bulk condensation from that happened. So we just got a huge layer of bismuth. So this is like on the order of microns. And like even the substrate was like white. So this is the optical microscope image. And so, well, that's not going to work. We're going to have to change something about the temperature. And so we started using a higher temperature. So we used 485 Celsius, then with bismuth 0.4, again, just homoepitaxy of gallium arsenide. And what we got was these quite smooth surfaces. I mean, if you look at the AFM, you can see the beginning of these smooth atomic terraces, and you can also see very similar shades. You can see it's quite smooth. Also for here, this is just a zoomed out version of the AFM. You can see how we get these very smooth step flow growth. And so this is just an animation of how the growth proceeds. And so you can see when we use this, we get this instead of these hillocks, we get this with this step flow growth. And this is just an animation of how the growth proceeds. And this really is indicative of how smooth this surface that we're creating is. And so again, just to drive the point home, we can see this is the surface that we got with bismuth, and this is an example surface of gallium arsenide one-on-one growth homoepitaxy without bismuth, and we can see clearly the atomic steps here, how uniform it is versus the hillocks that we're getting, like micrometer level hillocks. And so naturally, we wanted to increase the bismuth flux to see if we're going to get smoother surfaces. And so we continue this growth series with bismuth flux of 1 monolayer per second this time, rather than 0.4 monolayers in the previous slide, with same temperature. And what we get is even smoother surfaces. So bismuth is indeed really inducing these smooth surfaces and getting rid of these hillocks. And so we get these very smooth atomic terraces with no hillocks. And again, this phenomenon of step flow growth. And these steps are have relatively equal spacing, as you can see here, they're relatively even. And this is a phenomenon known as step anti-bunching. And so what happens here is the electrobial barrier is actually with bismuth, like when we use bismuth, it's actually helping us get these the step anti-bunching, or these equal spacing of the steps, because the diffusion uphill is easier than the diffusion downhill. And so there's a faster growth of the small steps and the slow growth of the large steps. So there's this driving force for equalization of the surface. So that was a pretty interesting find. And so now we know we can grow these very smooth gallium arsenide surfaces. And so one interesting application, one interesting thing we can do even before going into the whole concept of quantum dots is, okay, maybe we can grow some very smooth quantum wells, for example. We can, for example, then create, they can have very sharp line width emission. And so due to COVID, we started to think maybe we can do some modeling, with the lack of access to experimental facilities. We can start to do some modeling. And so we did some modeling for indium gallium arsenide on gallium arsenide quantum well, and just simulate the energy levels using this Schrödinger-Poisson solver or technique. And basically, just quickly go through the concept, is basically what this does is that it's a self-consistent solving technique. So what we do is we have an initial electron density of n, and then we solve the Poisson equation to get the electric field, which then has some influence on the potential. So that will change the answer we get from the Schrödinger equation, the wave function, and the n. Then we get a new electron density, and then as any iterative surface, repeat until it converges. We get the self-consistent solution. So it's this method to take into account the electric field and the Schrödinger equation together. And so we used for this a simulation tool called Crosslight. And this is the example quantum well that I modeled, just in-gas quantum well 5 nanometers. So this was the result. We got I got one confined electron state found around 0.64 eV. And you can see here 2 confined hole states. And so the next step was to then do some like modeling of the spontaneous emission rate as an estimation of the photoluminescence. And this is just room temperature photoluminescence, 300 Kelvin, like in the simulation. And so we did this at, or I did this at different carrier densities. So from 10 to the 15 all the way to 10 to the 25. And you can see as the carrier density increased, the width increased. So this was just an interesting like modeling scenario we made like during, or I made during COVID. And so now we know that we can create some surfaces. We've done some investigations on how a quantum well would a smooth quantum well look like. We now want to know how the how bismuth is actually acting as a surfactant. Is it, how well is it sticking to the surface? We need to know more about how it's influencing the growth. And so thin film growth is dependent on several thermally activated processes, like for example, diffusion and desorption. So you can see here, desorption is just the atom being released into the gas again from the layer. And this is a thermally dependent process. Same with diffusion across the surface. And we can have these energy barriers to translate that into equations. And so it's important to understand for growth and surfactant action, important to understand the desorption energy of bismuth on gallium arsenide 111. And so basically this is this Arrhenius, it's called an Arrhenius relationship. There's a relationship between the tau desorption or the desorption lifetime rate is equal to this attempt frequency. So this is the frequency of bouncing the atom, trying to get rid of the bond. And this term that's dependent on the temperature and the barrier energy. And so if you can take log both sides, you can start to see that we can get some sort of linear Arrhenius plot where the ln of the desorption rate versus an inverse of the temperature. We can guess this plot. We can then extract the slope, which is the desorption barrier. And so if we manage to calculate tau for different temperatures, we can then do this plot and extract the slope, which is the desorption energy, which is our goal. And so to do this, we need a tool called READ. This is stands for reflection high energy electron diffraction. And it's very important for in situ characterization of the growth. It's a very important tool in MBE to characterize how the growth is progressing as the growth is progressing. And so taking advantage of the vacuum conditions in MBE, we can have this electron gun. And basically what we do is we shoot this electron beam, and then it grazes the sample or the surface that we're growing. Then it diffracts, causes some sort of diffraction pattern. We can then capture this diffraction pattern with the camera, and then this pattern can be a description of what's happening on the surface. So if the pattern changes, then something on the surface has changed. And so basically the gist of the experiment is that we want to deposit bismuth and then interrupt the growth. As the read changes, we can determine the tau desorption for that particular temperature, then we can extract the slope. And to really to really elucidate a bit more on how this experiment went, so this is just a graph of the flux versus time for bismuth. And so we can see here, first we're going to have this, we have our gallium arsenide sample. First we're going to have bismuth off. Then we're going to start bismuth for 60 seconds to make sure it covers the surface. Then we're going to have bismuth off. And then here, you can imagine when there's no bismuth, there'll be a certain read pattern. During the bismuth deposition, there will be a new read pattern that will emerge. And then when we turn the bismuth off, we will return to the old read pattern when there was no bismuth. And that's when the bismuth all dissolves. And so the time it takes to change between this new read pattern and the old read pattern, really, this is an estimate of the desorption time, because this is manifestation of how the bismuth is desorbing. And so basically that's the essence. This is the gist of what we're going to do with this experiment. And so if we repeat this experiment for different temperatures, we can again get the slope as we mentioned. And so this is an example video of the read of this experiment that I designed and did at 485 Celsius. And so this is just a data point, if you will. And again, we start with the gas buffer layer. It has a certain pattern, as we can see here. So this is a picture of the read without any bismuth. So the moment it changes, there, sorry, the moment, let's go back. The moment it changes, there, that's the bismuth is now on. So the read has changed. So just to skip 1 minute in, this is all bismuth being applied, so no change in the read. The read is stable. But then suddenly, as you can see here from this circle, the read has changed back. That streak has reemerged, or that spot that we're mounting has reemerged. So what we want to do, because the bismuth has been shown, so what we want to do is we really want to see how long it takes for the streak to reemerge. But this is translation of how long the bismuth took to dissolve. And so this is what we did. So we plotted basically using some image and processing. We plotted just the change in intensity of this dot or streak, if you will. And so what was happening here? Is the bismuth is being deposited, and then once the bismuth is switched off, we start to see this time rise again to get the streak back to its original intensity. And so this time rise really is the essence of it is indicative of tau desorption. And so this is just two plots of two different streaks. And so basically what we want to do here is we want to fit this intensity, rise in intensity for the spot. We want to fit it, and for example, we can assume that it's rising exponentially. So we want to fit it with an exponential function, and then solve for or fit to calculate tau desorption at this particular temperature. So that's what we did. This is using MATLAB. I did some curving, and the tau desorption turned out to be about 1.55 seconds. So 1.5 seconds for the bismuth to dissolve in seconds. And so you can, as you can imagine, doing this for several temperatures, getting different tau values. And as you can see here, that it actually increases the more the temperature decreases. So that is logical. Takes longer the colder it is. And so just taking the ln of all these values and then plotting the linear Arrhenius plot, we can find, and taking this slope, we can find that the barrier energy is around 1.625 electron volts. Now, this is the first time that I think that the barrier energy has been calculated, the desorption barrier energy has been calculated for bismuth on gallium arsenide 111A. And gallium arsenide 111A is just basically the gallium terminated version of gallium arsenide 111. And so this tells us how the growth conditions, for example, the temperature, can really change the surfactant behavior. And so I just want to touch briefly on some work I've been doing on MOCVD due to some complications we've been having with the bismuth source on MBE. We just elected to try out MOCVD just to investigate how growth of gallium arsenide 111 works there. So gallium arsenide 111A homoepitaxy, this is again just homoepitaxy, using MOCVD or Metal-organic Chemical Vapour Deposition, is also plagued with hillocks, unlike 100. So it has the same problem. But interestingly, unlike MBE, we have this window of smooth growth that we can access here. So if you can see here, this is the arcene partial pressure, and this is the growth temperature. And like no matter what conditions you pick, you get hillocks and defects everywhere. But if you pick the right arcene partial pressure and the right growth temperature, maybe you can fall into this smooth region, which doesn't exist in MBE. And so, okay, that's interesting. Let's, without any surfactants or anything, let's just try and do some homoepitaxy on MOCVD and see what we get. Maybe we can fall into this mirror region. And what happened was, first we tried gallium arsenide 111A, again, the gallium terminated version of 111. And so we used the temperature from the conditions similar to that in the literature. And what we got was, you can barely see this on atomics terraces. It's relatively smooth, but still you get all these nanometer bumps, as you can see here. And when you zoom out, you can see that it's relatively uniform, but still it's quite bumpy. But the interesting thing was when I tried growing on 111B, and again, this is without surfactants. This is just growing just with just normal growth. And I used the temperature of around 720 Celsius, factor ratio of 40, and you can see you get these very, 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 very smooth atomic steps. And so this is like sub-nano roughness. This is like very smooth. Without even any surfactants. This was quite an interesting find, and this can be a very great platform for device or quantum dot growth. So you can imagine now you can start to use the indium arsenide with the surfactant to, instead of get 2D layer growth, create the 3D quantum dot growth, but this time on an actually good starting surface, like smooth. And so just quickly to touch on some future and current work that I've been doing. And so Again, like I mentioned in the previous slide, what we want to do in the future is now to start to use antimony. Antimony is, we don't have bismuth on the MOCVD, and we want to continue using the MOCVD. So basically, antimony has a similar effect to bismuth. So we're going to want to use antimony. So we want to start using antimony for on this very smooth gallium arsenide surface to induce these indium arsenide quantities. And so actually, funnily enough, antimony has been used already, but on 100. So 100 indium arsenide, gallium arsenide already yields quantum dots, but it's actually been used to increase the density, and this creates smaller quantum dots. So this decreasing, like for example, the probability of having a large quantum dot, which might plastically relax, create defects, not good. So you can see here, antimony has really, even on 100, it has an effect on creating more density of quantum dots. We want to, but it's never been used on one-on-ones. We want to just first, in principle, just see what it does on one-on-one within the master. Does it create quantum dots like 110, for example? We don't know. And so the interesting thing here is antimony has a tendency to incorporate more than bismuth. So there's going to be a more careful decision of how to choose the substrate temperature, just if we don't want it to be too low for it to incorporate. And so that's an interesting thing, growth that we can do in the future. So basically, yeah, the next step is to use antimony on gallium arsenide 111 A and B for quantum dot SK growth in the arsenide with these smooth starting surfaces. And finally, another direction we could take is to actually grow these smooth quantum worlds that are going to have this sharp emission that we've been talking about earlier in the presentation. And so we want to grow, for example, non-surfactant assisted in-gas quantum world, and one where we have to use bismuth to create smooth interfaces and surfaces, and see the difference in line width. See the diff, like, is there really going to be a dramatic change in the sharpness of the line? And so that's another interesting thing I want to do in the future. As well, we want to continue on the modeling that I've been doing and start to model, for example, a rough quantum world. You can see here, this is like an example of the interface of a rough quantum well, and we want to start, for example, you can imagine dividing into many small quantum wells and them having different emissions and playing a broad of spectrum. We want to start doing that model. And so just in summary, we have found that bismuth indeed acts as surfactants on 111, and we've managed to calculate the desorption energy using a real experiment, which hasn't been done before. And bismuth can induce these atomically smooth surfaces on previously defect-ridden gallium arsenide 111 step flow growth. We've shown that MOCVD can be potentially improved. The growth can be potentially improved using antimony, and it's already quite smooth. And these results indicate that surfactant-enhanced gallium arsenide 111 growth can constitute a solid platform for further device growth, especially in the gallium arsenide quantum dots for entangled photon sources. And thank you.
Okay, thank you.